Hello everyone, my name is Berk Erhan Yüksel. Today I'm going to answer the questions of homework 4, which name is structure and operation of a DC machine. In the first question, I tried to draw physical structures of DC machines by hand. If we explain the field components of a DC machine, it consists a stator part which is stationary, as you can see the stator part, and permanent magnets or coils to generate external magnetic fields. Some DC machines, the coils place the top leg and the bottom leg of the stator to generate electrically excited DC machine, or permanent magnets are used to generate the DC machine. However, permanent magnets are mainly used in DC machines because of stability and efficiency. On the other hand, the armature components are mainly four elements, which are the core, armature coils and windings, commutator, and the shaft. These four elements rotating parts, since they rotate with Lorentz torque by excitations. However, if you look at the inside of DC machines, we can see the brushes, which are made of coil and carbon, and the brushes are stationary also. The outer part of a DC machine is a stationary frame, as you can see, which protects the machine from external influences. Furthermore, the rotary bearings allow to utilize the rotating shaft in a fixed frame. To sum up, the field components consist of three elements: stator, coils, and permanent magnets. These are the stationary, and the armature components are the core, armature coils or windings, and commutator and shafts, as you can see. Uh, these are the rotating parts because of the armature rotates with the Lorentz torque in the DC machine. On the other hand, we have carbon and coil brushes, which is stationary, and frame that is stationary also, and bearings and other elements. In the second question, we can identify the type of forces into two groups in the DC machine. The firstly, the Lorentz force and the reluctance force. In this point, we need to say all magnetic forces that we have are the result of the fact that the magnetic field lines tend to shorten and minimum energy state. We have Lorentz force. Since we have a current carrying conductor, especially we have a lot of windings on the core, in the presence of external magnetic fields, we need to have the two actively excited parts, one to create external magnetic flux and one to excite the conductor. On the other hand, we have reluctance force on this DC machine because of conductor currents, but it is not utilized in force calculations and torque calculations. Therefore, we consider mainly the Lorentz force. As you can see, I drove the external magnetic field lines and take the one loop of the windings. By right-hand rule, this system rotates in the direction of clockwise. If we want to calculate the Lorentz force acting on a current carrying conductor, we need to use these formulas. We just know the number of turns, current, length of the conductor in the z direction, and external magnetic field, and the relative position. By tangential forces, as you can see, on the current carrying conductor, this system has a rotation and also torque. The brushes and commutators are the main factors of the DC machines to utilize effectively. As I mentioned in the second question, if the currents external B field are constant, when the half of the rotated part start to pass other side, the rotor will encounter a force opposite to the direction of the rotation. If the Q is equal to 90 degrees, as you can see, this system begins to rotate clockwise direction that can be seen from the first and second images. However, When the system passes to the other side, it encounters with the opposite tangential force that tries to rotate the system counterclockwise, as you can see, from clockwise to counterclockwise. Therefore, as can be seen from the graph, this graph, this system will stop after a while. To generate a continuous system, we need the brushes and commutators. The picture of this, the X part of the commutator reaches the negative terminal of brushes and the Y part touches the positive terminal. Furthermore, we have a rotationary commutator. Therefore, when the commutator starts to rotate, X part starts to touch positive and Y parts to negative. By doing this, we have always current into the page on the upper part of the rotator, and the current out of the page below of the rotator part. As a result, the rotor rotates continuously, if we neglect the leakage powers, of course. On the other hand, in the generators, a DC voltage is generated at brush terminals as a result of rotation and commutation. You can see the rectified coil voltage and brush voltage on the graph. This graph indicates that the voltage between brushes in the DC machine, according to my previous explanations. Furthermore, the brushes are stationary part and the commutator is a rotationary part, since the commutator rotates with the armature and shaft. If we look at the fourth question, the equivalent circuit of DC machine is like that. In the armature part, the left-hand side is armature terminal voltage VA, and right-hand side indicates the induced armature voltage EA. This voltage measured from brush terminals. Therefore, these voltages and current values are DC. Array indicates the copper losses of armature windings. On the other hand, in the field part, Aleph indicates the magnetically stored energy, and RF is the copper losses of field coils. As we can see from these equations, if VA is greater than EA, the machine starts in the motoring action, so electrical energy is converted to mechanical energy. On the other hand, if VA is smaller than EA, the generator action starts and mechanical energy is converted to electrical energy. If we look at the induced voltages are measured from brush terminals, and induced voltages can be found from these equations. As you can see, induced voltages are related to flux and rotating speed. Of course, V mechanical has unity radian per second. Induced voltages can be calculated as average voltage. Of course, Ka times flux, flux peak value of the flux is equal to machine constant. Also, R is indicate the armature radius, L indicates the axial machine length, and of course, we make is mechanical speed or armature or rotor speed. On the other hand, if we calculate the torque value, we can use these equations. As you can see, electromagnetic power is equal to armature power and minus armature losses. And we examine the torque value. The torque is equal to machine constant times IA. Of course, PEM, so electromagnetic power is equal to torque multiplied with rotor speed. Therefore, we put these equations into this and we calculated the torque as like. In conclusion, EA times IA indicates the electromagnetically generated power that is delivered to the mechanical system. Of course, as the result of this, induced voltage and torque both depends on machine constants, Ka times flux. In the last question, we examined the power flow in generator and motor modes by using equivalent circuit model. To obtain the output mechanical power in motor operation, we must subtract the mechanical losses from the electromagnetically generated power PEM. As you can see, P mechanical is equal to PEM minus P mechanical losses, and mechanical torque is equal to mechanical power divided by rotating speed V mechanical. We have three cases. Firstly, we have idly this case. In the real world, it's impossible. PEM is equal to P mechanical if mechanical losses are zero, so that is impossible. In the second case, electromagnetic power is greater than P mechanical. Therefore, our system operates in motoring mode. On the other hand, P mechanical is greater than electromagnetic power. System operates in generator mode. If we look at the motoring mode, our power input is electrical power. Because the current passing through the system, some copper losses or electrical losses and magnetic losses due to rotations happens. The result of these losses, electromagnetic power, converted to mechanical power by subtracting the mechanical losses into the system. In the generating mode, our input is mechanical power. Because of bearing friction and windage losses, we have some mechanical losses, as you can see. And generated electromagnetic power convert to output electrical power after electrical and magnetic losses. Um, in addition, we, as we mentioned before, we have in total three type losses. The mechanical losses and magnetic losses are due to rotation, and the magnetic losses consist of eddy currents that's proportional with frequency square, and hysteresis losses that is proportional with frequency. And the mechanical losses are due to friction and windage that is generated by rotating rotor in the system. On the other hand, in the equivalent circuit, we do only consider copper losses with sampled bits RA and RF, as you can see.